So, we now know how buoyancy works. If you have an object with a given volume, buoyancy is due to the pressure on the bottom being a little bit more than the pressure on the top, and it's equal and opposite to the weight of the fluid that would have been there if the object wasn't there. So it's the weight of the fluid that isn't there. Bizarre, but true. So, can this help us make a flying car? So what's the buoyancy force in a flying car? Let's say if we fill it with helium. So let's say a car, I don't know, maybe it's about 4 meters long for a big car, 2 meters high, 2 meters wide. And let's imagine that entire volume was filled with something like helium. Now helium is about 10 times less dense than air, so we'll just pretend it's like no density at all, which would be the buoyant force you got if you had that volume filled with a vacuum, and it's going to be pretty close to what you get from helium. So the buoyancy force is going to be the weight of all the air that would have been in the car before we pumped it full of helium instead. So the volume is about 2 by 2 by 4, which is about 16 cubic meters. Density of air is about 1 kilogram per cubic meter, roughly speaking. So we've displaced about 16 kilograms of air, roughly speaking. But a car has a mass of about 1,000 kilograms or more, say 1,500 kilograms. So that's about 1% of the car mass. This is pretty extreme. I mean, if having a 2 by 4 by 2 meter area, that's bigger than the interior cavity of most cars. And even that, even if it's sort of the vacuum or helium or something like that, which would be extremely inconvenient, you have to wear gas masks to be inside a car like this, is only going to reduce the weight by 1%. So, that's not going to work, or not going to make any significant difference. So what we're going to need is a much bigger volume. So we're looking at something maybe like this. Here's our car. To get 1,500 kilograms, is basically going to need 1,500 cubic meters. That's roughly a 10 by 10 by 10 meter volume. So that means if you've got our car here, what we're going to need is a balloon that looks something like that, or even bigger. Have some ropes to tie it down. So that's not looking very practical. Is that calculation right if we'd stuffed something up? Well, if you look at real hot air balloons, like here, you can see that yes, indeed, the volume of the balloon is much bigger than the volume of what it's lifting up. Now, hot air doesn't have as low density as helium. If it was helium, you can get away with a smaller amount. But nonetheless, the lesson is true. To lift something, you need a much bigger volume because the density of air is much less than the density of most things you're trying to lift. So would something like this be feasible? Cars with huge balloons over them. I mean, they wouldn't fit in the garage. It'd be hard to park. But that doesn't mean it can't work. Let's imagine we had something like this in our front. We could go up and float away to work every day. That would be worth having a big garage for. But unfortunately, there are a number of problems. One big problem is that this has a huge cross-sectional area. So if it's like 10 by 10 meters, that's about 100 meters squared cross-sectional area, compared to a car which might be like 2 by 2, which might be 4 meters squared. So it's going to be about 25 times greater cross-sectional area. Now, if you remember, the drag force depends on the cross-sectional area. So instead of needing, say, 10 to the 8 joules to overcome drag force and get to Sydney, you're going to need 25 times that if you're going at 110 kilometers an hour. So what that means is drag forces are going to be an absolute killer for cars supported by giant balloons. First you have to have trouble parking them, and then the drag force is going to be absolutely colossal unless you go slower. So if you remember, the drag force is proportional to the area times v squared. So if you increase that by 25 times, to get the same drag force, you have to decrease that by 5, because 5 squared is 25. So instead of going at 110 kilometers an hour, you'd be going 5 times less, so maybe about 20 kilometers an hour. So what that's telling us is that a flying car controlled by a balloon, it's going to have to go pretty slow. The other trouble is wind speed. Winds of 20 kilometers an hour are pretty common, and it's a good fraction of the days you'd have a wind that strong, and that is going to apply huge drag force. Remember, drag isn't just you moving through the air, it's the air moving past you as well. It'll be very easy, unless your car is very well moored down, to find it's been blown away in the morning when the wind comes through, or when you wouldn't be able to commute to work if you're facing into a headwind, or it would take 5 times as long. So these are actually all the familiar problems that airships have had over the years. They have to be very, very large, they can't go very fast, and they're very vulnerable to wind, and they're hard to store anywhere. So is this the answer to flying cars? Well, I mean, you can make a flying car like this, but because of its enormous size, enormous drag, it's not going to be very feasible.